Since the participants are not too many, so we wait for a few more minutes to see until the reasonable students join this meeting. Can be 5 to 10 minutes. All right, so we got enough participants. Let's take start. Bismillahirrahmanirrahim. Thanks for Allah subhanahu wa ta'ala for all his blessings and bounties that he has bestowed upon us. Which of the blessings of your Lord will you both, jinn and insan, deny? So Alhamdulillah, we should make shukr to Allah subhanahu wa ta'ala who has given us one more day, one more chance to repent to Allah subhanahu wa ta'ala. How do we repent to Allah subhanahu wa ta'ala? by thanking whatever He has given to us, whatever He has bestowed upon us. So, if we look back into the lecture previously, we have discussed different types of the first order differential equations and different types of the higher order differential equations, and also techniques available to handle them. Now we are going to talk about applications, talking about real world phenomena, talking about practical demonstrations from our daily life. Here, but we will try to cover as much as we can. I let once you log in, very first thing that mute your microphone. All right. So there are plenty in our daily life. Differential equations are of fundamental importance in science and engineering in particular because of many reasons. When we look into physical laws, relations, they normally appear in the form of differential equations. Particularly when we talk about engineering discipline, so we say that when we are interested to make the physical phenomena to be expressed in the form of mathematical formulation, the mathematical formulation of every engineering problem will turn out to be differential equation. So this is known as modeling. First of all, we look into the phenomena and then the transformation. We look into the mathematical formulation. This is known as modeling. Once the model is there, the mathematical model is there, then we look into the implementation of any of the available techniques behind the scene. Depends upon the nature of the equation, the order, and specific type of the equation. We apply a viable option behind the scene to simplify that particular differential equation. So when we look into the solution of that particular differential equation being modeled from the physical phenomena, it will take us to the solution of the original phenomena behind the scene. And when one very vital thing to be noted down, whenever there is a limit, the concept of limit is involved. The solution can't be exact solution. It is going to be an approximation. Because all we know about the concept of limit, it describes or shows the behavior of a function around a point, not exactly at the targeted point. So when we are around the targeted point, so it is going to be an approximation. And we know that based upon the concept of limit, we describe derivative. And from the process of differentiation, we move on to the differential equations. So eventually, we are talking about differential equations, but behind the scene, the starting point is the limit, the concept of limit. So this is how we say that the foundation is there to talk about limits, to talk about the concept of differentiation. They are heavily based upon the concept of limit. So this is how when we talk about the solution, so it is going to be an approximation. We will look in it in a few minutes. But the idea is that whenever we find the solution, it is going to be an approximation. So we will try to discuss the derivation of differential equations from physical phenomena. So phenomena is there, and we are going to transform into the form of differential equation, the mathematical formulation, which is known as modeling. A great importance, great practical importance to engineers, has great practical importance to physicists as well as to computer scientists. So if we translate a physical phenomena to a mathematical model, then quite often we obtain a set of differential equations along with certain constraints, conditions. So whereas the solution of the system of differential equations will provide us the solution of the actual problem, the solution of the actual phenomena. So our target in this particular topic is to take physical phenomena. We'll try to make mathematical modeling in the form of differential equation, and then from the differential equation we will find the solution. But the solution of differential equation will actually be the solution of the physical phenomena. Quite a few applications are available in the literature, but we will try to discuss more important or the one that are frequently utilized in our daily life. Population model. Everywhere we are looking for the observation about the population of certain community, the population of certain town, the population of certain country, the population of the world, and so on. How we do that, it is all based upon the concept of differential equations. Description is there. If relatively small populations, either of human being, animals, bacteria, whatever the kind is, are left undisturbed, they often grow according to Malthus rule, named after the English social scientist, which states that the time rate of change of population of a country, of a town, of a community is directly proportional to the population present at any given time. So the rate of change of population is going to be proportional to the population present. So this is all. The rule is there, the law is there. So based upon this rule, based upon this law, we will develop a differential equation behind the scene. So as a symbolic representation, let n, since n describe the number of population, so it is going to change with time, so it has to be function of time. N of t means it is going to change with respect to t. N depends upon time. Time is going to be independent variable. N is going to be dependent variable. It is going to depend upon the corresponding values of the variable t. So t is going to be independent. So this is how we symbolically represent the population of certain community as capital N of t. So is the population that is either growing or decaying. I mean, these are the two possibilities behind the scene, because it has to change with respect to t. Either it is going to be increased with time, or it is going to be decreased with time. So when n is function of t, so there is only one possibility behind the scene to get a change in the dependent variable. It should be with respect to t to have a non-zero change. So the time rate of change of n with respect to t is going to be dn upon dt. Remember, still n is a function of t, but for simplicity we just mentioned dn. Otherwise it should have been n of t. Now, if you look into the implementation of the law described over here, what the law? The time rate of change of population, the time rate of change is dn upon dt, is directly proportional to the population present. and we assume that the population present at any time is n, whereas the rate of change is going to be dn upon dt. So they are going to be directly proportional to each other. In other words, we say that the population is going to be changed with respect to t. The time is going to be independent. With the time, the population is going to be changed. Could be increased or decreased with respect to t. So change in the population is proportional to the present population. Get rid of constant of, the proportionality sign by introducing a constant of proportionality. Now we have the equality sign. dn upon dt is equal to kn. So it's the first order differential equation because of the equality sign, differential equation because of the derivative involves of the dependent variable with respect to one independent variable. So if we assume that the initial population of that community is n naught, means when time is 0, the population of the community is a fixed number. Symbolically, we assume that it is n naught. So in this way, we will be having the initial condition. Initial condition means for the starting value of time. So we have assumed the starting time as 0. So n of 0 is equal to n naught as a symbolic representation. So in this way, we have an initial value problem. A problem together with initial condition is going to be described as initial value problem. So much easier to look into the solution. We know that it's a variable separable form, the most easiest, the most fundamental among all the first order differential equations. Separate variables on either side, look into the integrals, and then eventually apply the initial condition to get rid of constant of integration. We will be having the solution. N of t is equal to n naught times e raised to power kt. Now you see that the population is going to be changed, n of t, based upon this combination. So it is going to be multiple of the initial population, e raised to power kt. The exponential function e raised to power kt increases as t increases for all k greater than 0, positive values, and decreases as t decreases, because in this way you need to take it in the denominator, something divided by denominator is going to decrease that value. But if you multiply it, of course, it is going to be increased with the passage of time for certain conditions. K is greater than 0. Thus, in problems describing growth, when the population is increased, K will have a positive value. Whereas in problems involving decay, such as radioactive disintegration, K will yield a negative value, pretty much on the same way. And is similar to that of population model. We could also look into the modeling for radioactivity exponential decay, atmospheric pressure exponential decay, and many others, pretty much on the same line. So you see that eventually we see that a model is going to be first order differential equation, and most probably it is going to be variable separable form, could easily be handled by separating variables. We know the technique behind this. How do we handle it? The most simplest, the most basic fundamental technique among all the techniques available to solve first order differential equation is the starting one, the variable separable form, where we separate the variables, then look into the integral on either side with respect to the variable of integration. All right, take an example. So this is all. The model is there. We will base upon the law, states that the time rate of change of a population which is going to grow or decay with respect to time is proportional to the population present at any given time. So this is the rule, this is the law. Based upon that law, we will see that it will turn out to be differential equation of first order. And from there, we need to simplify it. Take an example. The population of a certain community, of a certain town, for example, was 1,000 1 year back, and the present population is 2,000. What will be the population of the town after 3 years? 1 year back, population was 1,000. At present, the population is 2,000. So when will be the population of the town after 3 years? I mean, just imagine, we are talking about the population of a country. So now 1,000 with whatever the units are there, that could be 1,000 million, 1,000 trillion, whatever it is. So it is just a number behind the scene. So imagine we are looking for the population of this country right now based upon the data provided from the previous year. And the previous year, the population was something like this number. Now the population is that much. What can we expect the population of the country after 3 years? So this is how the extrapolation is done. We forecast. We somehow imagine what could be an approximate number after a certain number of years. All right, so the model is there. But the model is there. So eventually the model is going to be that one. If you label the population, if you label the rate of change, eventually the mathematical formulation or population model will be that one. And then the solution is going to be that one. I mean, it's a pretty obvious thing. Just go back with variable separable form and you will easily get down with this form. So initial condition states that. So 1 year back, the population was that, now is that, and then we are interested to find the population, means we are interested to find n when t is equal to 3. So keep an eye on these conditions. We look into the model. Let n be the population of the town at any time t, since the initial population was 1,000. So this is the starting point, 1 year back. We can say that, yes, n is equal to 1,000 when t is equal to 0. This is the starting point, 1 year back, 1 year back. The population was 1,000. If unit of time is year, so then after 1 year, means from 0 to 1, the population is doubled than what it was 1 year back, 2000. Since the rate of growth dn upon dt is proportional to the population present at any time t, so we will be having this equation, the mathematical model. dn upon dt is equal to k times n. K is going to be constant of proportionality. The solution of this equation could easily be obtained by separating variables, and eventually we will be having n of t is equal to capital A times e raised to power k, where you could represent e raised to power c, I mean the combination of two constants, by another one, more suitable, more viable. A stand for e raised to power c. It's a combination of two constants. E fixed value is there, and c is going to be arbitrary. So we just replace them. So eventually we will be having a times e raised to power kt is the general solution of this equation. Because of the number of arbitrary constants equal to the order of the equation. It's a first order, and we have only one arbitrary constant, a. So this is obviously that this is going to be the solution of equation number 26. Using the initial condition. What the initial condition? Over here, when t is equal to 0, n is going to be 1,000. So when t is equal to 0, so e raised to power 0 is 1, a is equal to 1,000. So this value If you take this value, plug in over here, so it will turn out to be n is equal to 1000 times e raised to power kt. So this is all. And it was stated currently means after 1 year from the previous condition, when we take start 1 year back. Now at present the population is 2000, means when time is 1 year being the unit behind the scene. Time lapse 1 year and the population is doubled, implies that, so now apply this condition on that particular equation when t is equal to 1, n is equal to 2000, plug in the value of n, 2000, and the value of t as 1. So we will be having this thing. Many ways we can simplify this one. Our target is basically to find k, but we could also replace this whole combination because it will involve. So e raised to power k is going to be 2. So we have this expression. So it is e raised to power kt. So separate the power t, and inside the bracket e raised to power k is going to be replaced by 2. So our expression is going to be that one. It's a very nice expression now. I mean, after doing all the hard working, solution, general solution, from the general solution, we look for the arbitrary constant, applying the second condition, and eventually we see that this is going to be finally the relation between the dependent and independent variable. No, we can go either way. If you are interested to find the population after a certain period of time, just plug in the value of that small t being the year. Or if you are interested to observe time to attain certain number of population, so you just replace capital N. So whatever the way that you look for, from this relation we can observe the population by providing small t, or we can also observe time by providing population of the community. So either way, our target is to find the population as an approximation after 3 years. Now remember, 3 years from right now. But when we started off, we started 1 year back. So our time started 1 year back. So from right now, 3 and 1 back. So in total time lapse will be 4 years. And therefore, when t is equal to 4, what could be an approximate population of the community? So plug in the value of small t as 4, simplify this one. So this approximation is going to an approximate value, approximate number of people, because this is just a guess. We just presume that if things go on pretty much on the same pattern that we are expecting, so eventually it is going to be 16,000 approximately. Could be 16,005, could be 16,010, or 59,990, whatever it is. This is an approximation. Nobody knows the exact figure, of course, except Allah subhanahu wa ta'ala. So this is all. We model the population of a certain community as a forecast after a certain year. If things go on in that particular fashion, so it is going to be approximately that thing. So we are saying that yes, the figure was there. I mean, 1,000 is there. You could change to 1,000 million, for example. You could change town to community. You could change town to country. You can change town to the population of this world. Just model is there, play around, and this is how you can extrapolate. I mean, you often read in the newspaper that yes, the population of this world is going to be that much in 2025, in 2050, for example, 30 years from right now. So how we do that? Based upon the concept of differential equations. Model that, simplify with the assumption based upon the provided data, we move on. All right, so take an example. So this is the complete description of the problem. Physical phenomena was there. We look into the mathematical modeling with certain conditions. No, with the help of certain conditions, we get down with the solution. No, this is the solution basically of the differential equation modeled based upon the physical phenomena. So we say that this is an approximation. The figure for the population of a town, that physical phenomena is there. So it's basically the solution of that phenomena. Take another example. The population of a certain country is known to increase at a rate proportional to the number of people presently living in that country. This is all. I mean, the rule is there. The time rate of change of population is directly proportional to the population present at any time. So in the first sentence, this is basically the description of the same rule. If after 2 years, population has doubled, and after 3 years, the population is 20,000, find the number of people initially living in the country. Different demand is there now. We don't know. I mean, if in the previous example, we have forecasted the extrapolation. We look into the future somehow. Now we need to go back. Right now we have the information. After 2 years, population has doubled, and after 3 years, the population is going to be 20,000. You need to go back and find the population in the previous year. For example, we are in 2020. You are interested to look into the population of this country in the year of 1991, for example. Yes, it is possible. Somehow you can look into that based upon the piece of information, based upon the data provided to you. We can go back as well. Not only we can look forward, but we could also go back. As an example, this one. So you need to try. Take start from the same mathematical modeling, label the initial population like N naught. I mean, as a symbolic representation, as you have seen in the article. What is N naught? N naught is the population when T is equal to 0. So you need to take start from here. Let N naught be the initial population. Initially, you need to take start by following this mathematical model. You have to take start from here. Eventually, you will be having this differential equation with constant of proportionality. If we assume the initial population to be N naught, so eventually we will come down to this solution. Form of the solution is there. And this is how you need to apply those conditions. What is the condition? If after 2 years, population has doubled when T is equal to 2, so if you assume the initial population is N naught, so after 2 years, when T is equal to 2, the population is doubled 2 times N naught. And after 3 years, the figure is given. And this is all you need to find the initial population. Means you need to find N naught. And you go with the answer. The initial population is approximately 7,062. I mean, this is an approximation. All right, so next examples. If the growth rate, I give you an idea about the examples. If the growth rate of the number of bacteria at any time t is proportional to the number present at t, any time t, and doubles in 1 week, again, half part of the sentence is the rule. The law, the population, the law of growth behind the scene. If the growth rate of the number of bacteria at any time t is directly proportional to the number present at any time t, so this is the law of growth basically, and doubles in 1 week. No, the units are going to be changed. I mean, bacteria could rapidly change their population in comparison of human being. So they are going to double in 1 week, assume that. How many bacteria can be expected after 2 weeks? Second part, how many bacteria can be expected after 4 weeks? So pretty much on the same line. You need to take star. Same symbolic representation you could take, like n of t is the population of bacteria at any time, and naught is the initial population. When t is equal to 0, the population is going to be n naught, and doubles in 1 week. Now the units are going to be week. When t is equal to 1, n is going to be 2 times n naught. And you need to find an approximation about the population of bacteria after 2 weeks when t is equal to. So it will turn out to be something like that, 4 times n naught. The initial population is unknown. So what the answer is there? After 2 weeks, the population of bacteria will be 4 times the initial population of bacteria. It's unknown. Whatever the number is there, after 2 weeks, the population is going to be 4 times. And after 4 weeks from right now, it's going to be 16 times the initial population of bacteria, whatever the number is there. So if you know the initial population, you will get a figure over there, approximate figure over there instead of symbolic representation. Next, a bacterial culture. Next example, a bacterial culture is known to grow at a rate proportional to the amount present. Again, highlights of the law of growth. After 1 hour, again you see that the units are going to be changed. Sometime it's in years time, in week, in hour, whatever it is, forget about that. You need to concentrate on the figure 1 hour. After 1 hour, 1,000 bacteria are observed in the culture, and after 4 hours, 3,000, after 1 hour, 1,000, and after 4 hours, 3,000. Find an expression for the number of bacteria in the culture at any time. Means you need to find the relation between the dependent variable capital N and time. So based upon the same idea, apply those conditions. After 1 hour, 1,000 is the number of population. After 4 hours, 3,000 is the number of population. Get rid of all sort of constants over there. The arbitrary constant, the constant of proportionality, once you get rid of them, so the approximate figure is going to be that one. Not the figure effectively. Effectively, it's an expression there, multiple of 694. Capital N is equal to 694 times e raised to power 0.3663. So if you know the time, plug in over here, you can get an idea about the population after certain hours, because the unit is going to be hour in this case. Next example, between 8 a.m. and 9 a.m. time is there. The population of a bacterial culture tripled. I mean, if you assume that at a.m., early in the morning, if the population is n naught corresponding to t is equal to 0, then after 1 hour, when t is equal to 1, the population of a bacterial culture is tripled. So when t is equal to 1, capital N is going to be 3 times n naught. At what time will the population be 100 times of what it was at 8 a.m.? At 8 a.m., we assume the population is n naught. So now we are interested how much time it will take the population to be 100 times of what it was initially present at 8 a.m. So around 12:20 p.m., I mean after 4 hours, 20 minutes, for example, roughly, the population will be 100 times that of the population at 8 a.m. I mean, at 8 a.m., population is there and not. So we are interested to find the time it will take to get the population be 100 times. So when the population is 100, means capital N is equal to 100 times N naught. The corresponding time is going to be 4 hours 20 minutes, for example. So 4 hours 20 minutes from 8 a.m. means it is going to be 12 hours 20 minutes p.m. Change the time from a.m. to p.m. now. Next example, a mold grows at a rate proportional to itself. Mold means a kind of fungus. A mold grows at a rate proportional to itself. At the beginning, the amount was 2 grams. In 2 days, the amount increased to 3 grams. Find the amount of mold after 8 hours. Pretty much on the same line, of course. You need to look into the mathematical modeling. Conditions are there. Initially, when t is equal to 0, the amount is 2 grams. When t is equal to 2, now the units are going to days. After 2 days, the amount is increased to 3 grams. So this is how you apply the conditions. When t is equal to 2, n is going to be 3, and this is how you have to find the amount of mold after 8 days. So now the answer is approximately 10 grams. Initially, 2 grams. After 2 days, 3 grams. And after 8 days, it is going to be 10 grams. Another example in a different area. People look into the banking system. The interest problems are there. Forbidden for us, being Muslim. But anyway, we have to deal with this scenario. If 10,000 rupees are invested with annual interest of 10%, very, very harming. If 10,000 rupees are invested with annual interest of 10% compounded continuously, what will be the total amount of 5 years? This is how you get the interest. It depends upon the person. If 10,000 rupees are invested initially, you deposit that much amount into the bank, and bank offers you an interest rate of 10%, which is continuously compounded, which is continuously added. This is the rate of interest. 10% means 1 by 10 of the change. What will be the total amount after 5 years? That's a practical demonstration. If somebody is interested to observe his wealth, at present he has got a certain amount, like for example, it's a figure, 10,000, and he or she, that person, invests that much amount into the bank, and the bank offers that much rate, interest rate, and is expecting what would be the total wealth, total amount after a certain number of years. So you need to approximate that. Eventually, it will turn out to be approximately 16,500. So 10,000 right now, after 5 years, with that much interest rate, it will turn out to be approximately 16,500 rupees. All right, so keep an eye on these contents. You must have received the lecture slides before attending this meeting. So be there to download those files before you attend the lecture, because I try to upload this one at least 1 day before the lecture. In the meanwhile, I look into the attendance by taking a few minutes break. I generate a poll for you people to mark your attendance. There is a query. So please share slides with us so that we can practice and understand at home. It's there. It's there. I mean, all the lectures are uploaded over there. I mean, the present slides are also uploaded. I think, I mean, sometime yesterday I uploaded the file. So go and download the file from there. Why are we eliminating k from the power of e? Because it's unknown. It's unknown. Has to be some proportionality rate. The constant of proportionality is there because you need to balance things when things are proportional to each other. So at what value of the constant we can make the model in the form of equation. I mean, they are proportional to each other. For example, if one thing is going to increase at a certain rate, how do you adjust them in the form of an equation? So with a certain amount, with a certain scalar multiple of that amount. So that scalar value is going to be constant of proportionality. All right, yes, there is a query. Yes, they are already in file section. Go and get them from there. All the previous slides are there. On YouTube, lecture videos, I talked to one of this year, haven't received the feedback. I tried to talk to him, I mean, to look into possible ways, because I shared with him the lecture video. So I haven't received the feedback. So we were looking for the outcome, what should be the most appropriate way to get down with the option behind the scene. Anyway, I talked to them today as well. Let me create a poll for you people to mark your attendance. Attendance, it's 1st of July. Today is 1st of July 2020. So we are interested to mark all present people. Don't want to have the second option. Okay, there you go. So results are visible to everybody. All right, so we move on to another vital application in our daily life. When we talk about applications of ordinary differential equations, in particular, Newton's law of cooling. Newton's law of cooling states that the time rate of change of temperature of the body is proportional to the temperature difference between the body and the surrounding medium. Very interesting to understand the thing. Yes, if you are sitting inside the room with cooler on, with fan on, with the air condition on, so depends upon the scenario. The temperature of the surrounding medium means the temperature of the room does matter. Not only the temperature of the body, but also the temperature of the surrounding medium. So entirely different scenario to a person who is standing outside the room under the sunlight, for example, has got entirely different structure. So not only we need to observe the temperature of the body, but also we need to observe the temperature of the surrounding medium. In the first case, surrounding medium is the room temperature. In the second case, the surrounding medium is the environment where you are standing, maybe under the sunlight or somewhere else. You need to look into the temperature of the surrounding medium as well as the temperature of the body. So what the rule says, the time rate of change of temperature of the body. So how does the temperature of the body change? Proportional to the temperature difference between the body and the surrounding medium. So the time rate of change is going to proportional to the temperature difference between the body and the surrounding medium. So assume that as a symbolic representation, capital T denote the temperature of the body at any time, and capital Tm as a symbolic representation denote the temperature of the surrounding medium at any time. Means capital T and capital Tm are going to be function of T. Temperature most of the time, but we observe the temperature of the surrounding medium is going to be fixed. To make things simple, you could also take it as fixed value, but capital T is going to be function of T, is going to change with time. Then the time rate of change of the temperature of the body is going to be dt upon dt, because this is how we look into the rate of change, the derivative, the instantaneous rate of change, is going to be described by the derivative. And Newton's law of cooling can be formulated as what the rule says. The time rate of change of temperature of the body is proportional to the temperature difference between the body and the surrounding medium. So the difference between them is T minus Tm. So dt upon dt is proportional to capital T minus Tm. Get rid of constant proportionality sign by introducing constant of proportionality K, just like in the previous example. The law of growth, we have introduced the constant of proportionality. So capital dt upon dt with equality sign will be K times difference between the temperature of the body and the surrounding medium. With negative sign is vital. Where we have denoted the constant of proportionality by minus K in order to make dt upon dt negative, because what we observe, the temperature of the body is going to decrease with the passage of time. To make things compatible with the scenario, if somebody comes inside the room temperature is fixed, but your temperature is too high, note down your temperature of your body, note down the temperature of the room, and eventually you are expecting with the passage of time, the temperature of the body is going to calm down, is going to decrease. And that's what is the Newton's law of cooling. Body is going to cool down with the passage of time. To ensure that change is going to be negative, means if the temperature is, for example, certain degrees centigrade, once you enter into the room, after a certain time, the temperature has to, the change should be negative in order to make the temperature calm down. In order to make temperature decrease, the change should be negative from the point when you enter into the room. So this is a negative sign is there. We could also write it down, minus KT, take it to the other side, KTM. No, if you look into this form, so it's a linear first order differential equation in the dependent variable capital T. So linear differential equation in the dependent variable capital T. And we have gone through with the idea in the class that this could also be handled like variable separable form. Temperature of the surrounding medium is fixed. Temperature of the room is fixed. Just like you turn on your AC inside the room with a certain degree of temperature to be fixed. So to maintain that particular temperature, this is a work done by the AC. So it means that the room temperature is going to be fixed, Tm is going to be fixed. So you could also handle this equation by utilizing the very first technique, the variable separable form. Another point to be noted that capital T should be greater than capital Tm. The temperature of the body, the temperature of your body should be greater than the temperature of the room. This is only possible to get the body calmed down with the passage of time. If your temperature is smaller than the temperature of the surrounding medium, means the temperature of the room, your temperature cannot get down further because the temperature of the room will definitely affect the temperature of your body. So we are expecting to calm down the temperature of your body. It is only possible if the temperature of your body is greater than the temperature of the room, so that it is going to be compatible with the temperature of the surrounding medium after a certain amount of time. This law was verified experimentally by Newton way back, maybe more than 300 years back. So eventually, when we look into the Newton's law of cooling, our mathematical model is going to be first order differential equation could be handled either by using a variable separable form, the technique available, or by looking into the linear first order differential equation. From there, you need to find the integrating factor, and then the product of the dependent and the integrating factor is going to take you to the solution of the given differential equation. We all know about the criterion behind this, and how do we simplify this one. Now it's up to you. Because now we are not going to revise all those things, all those simple things which we have practiced over and over again in the classes. Idea is a mathematical model for second phenomena. When we are interested to make the temperature of the body decrease with passage of time, we have to follow Newton's law of cooling, and eventually the mathematical model is there. What we observe about this equation number 27, the equation number 27 is our first order linear differential equation in the dependent variable capital T. The solution of this equation is going to be that one. Whatever the option that you apply, either the variable separable form, make it variable separable form, separating variables, look into the integral, and then the constant of integration is there, or by using second to last technique, probably before Bernoulli's equation, linear differential equation of first order, get down with the solution. If the initial temperature of the body is assumed as T0 as a symbolic representation when T is 0, of course, when you enter into the room, This is how the time starts. When you just enter into the room, this is the time, the stopwatch. You need to click that. Time is 0 at that time. So this is all the surrounding medium. The temperature of the room is going to affect the temperature of your body. If you are outside the room, it won't make any difference to your temperature, because the surrounding medium is outside the room now, has got different environment. Only when you enter into the room. It is just pretty much the same example. If you take a glass of water and place it on top of the fridge, for example, will you expect this glass to be cooled down? You can't expect to get a cold water even after millions of years, because it's outside the fridge. But on the other hand side, if you place it inside the freezer, the upper portion of the fridge, or inside the lower portion, after a few minutes, few hours, you will see that yes, the water is going to be cold. So the effect is going to be monitored once you enter into that environment. If you are standing outside the room, the temperature inside the room will not affect your body's temperature. It will only affect once you enter into the room. So this is how the time will start. Your stopwatch start clicking. So assume that when you just entered into the room, T is equal to 0, and your temperature is T0 as a symbolic representation. Then from the above equation, from this equation, T is 0 and capital T is T0, get the value of C, T0 minus Tn. So place this value over here. Once you plug in the value of C and that equation, so our expression would be something like that. Something like that. I mean, depends upon the scenario, depends upon the condition that you plug in, depends upon the amount of T0, Tm, and K, stuff like that. You will get down with the relation between the temperature of your body and the time. So depends upon the requirement. Either you are looking for time to get your temperature down to a certain amount, or you are interested to observe your temperature of your body after a certain amount of time. So this is how eventually we will observe either time or temperature of your body. In the above formula, it is assumed that Tm remains constant, I mean, most of the time, to make things simple. Otherwise, of course, you see that sometime AC trip down. I mean, if it attains certain temperature in the body, maintain that, so it trip down AC in your room. So, I mean, fluctuation is there, possibility is there. The temperature could come down, I mean, or increase. So, but to make things simple, we are not, of course, that much professional behind this to observe each and every petty thing over there. But we will try to take glimpse of idea what are things to be important to us to observe that scenario. So it is assumed that the temperature of the surrounding medium remains constant at all time, and also the heat flows rapidly enough that the temperature of the body is the same at all points of the body at a given time. This is another assumption behind the scene, that the temperature of the body is the same at all points of the body at a given time. I mean, for example, you have terrible experiment outside the room. You are frustrated, for example, the temperature of your head is too much in comparison of temperature of your heart, for example. But what we will observe that the temperature fall at all points of the body is going to be steady. So with these assumptions, we move on. You can see that, okay, with these assumptions, there could be, I mean, the contamination in the solution. We are not observing the accuracy as it should have been there. But our target is here. We are talking about the glimpse of idea, what the scenario is there. With a little bit sacrifice in accuracy, we can get down with the answer. But of course, I mean, if you're more professional, you need to take care of those scenarios as well to get down better and better accuracy of the answer. We will look into the approximation. Assuming with the assumption that the temperature of the surrounding medium is constant, the temperature of the body is also same at all points of the body at a given time. Newton's law of cooling is equally applicable to heating as well. So what we observe when we talk about Newton's law of cooling, we should have a negative sign that the temperature is going to decrease with the passage of time. dt is negative, change is negative. So if the change is negative, it means that your body is going to calm down with the passage of time. To the other end, if you are interested to observe the temperature is going to increase with the passage of time, instead of Newton's law of cooling, we are observing heating effect, then you don't need to have negative sign. And in this way, to the other end, the temperature of the surrounding medium should be greater than the temperature of the body. Means Tm minus T will be there. Tm minus T will be there. This is one way to look into the observation. Other way around, taking negative common from this bracket, and it will make everything positive to the right hand side. The shortcut is there. Otherwise, things are there. dt upon dt should be positive. Secondly, temperature of the surrounding medium should be greater than temperature of your body. This is all. The temperature of your body will increase with the passage of time. For example, if you are standing inside the room with AC on, with cooler on, with fan on, and you go outside the room, outside the house, outside the building, and expose yourself under the sunlight. So with the passage of time, the temperature of your body is going to be increased. So when the temperature of the surrounding medium is greater than the temperature of your body, so we have developed the criterion behind the scene when we look into the implementation of Newton's law of cooling. But if you are interested to look into the other way around, to observe the heating effect, the mathematical modeling in that particular case would be like that. dt upon dt with positive sign, and temperature of the surrounding medium is greater than the temperature of your body. So in this way, the temperature of your body is going to increase with the passage of time. Take an example. A cup of coffee was initially boiling at 120 degrees centigrade, for example. It was placed in air at 20 degrees centigrade. You see that the temperature of coffee 120, temperature of the surrounding medium too low, 20 degrees centigrade only. After 10 minutes, the temperature is going to calm down with an amount of 80 degrees centigrade now. After 10 minutes, what will be the temperature of coffee after another 20 minutes, for example? What will be the temperature of coffee after another 20 minutes, I believe? Let me double check this statement, because after 20 minutes it will turn out to be 30 minutes. I might have to check this one. After 10 minutes, 80 degrees centigrade. And what will be the population, what will be the temperature of coffee after another, I think it should have been 10 minutes. let the procedure is done before we look into that mistake, typographical error. Okay, scenario is there. Temperature of the coffee is there, 120 degrees centigrade. When the temperature of surrounding is 20 degrees centigrade, and then we move on to the conditions. Let T is the temperature of coffee at any time. Then we know that the differential equation of Newton's law of cooling is going to be that. And we have already gone through with that model. But the equation is going to be that one, dt upon dt minus kt minus Tn, temperature of the surrounding medium. In this case, temperature of air is 20. So this equation will turn out to be that one, minus k T minus Tm is replaced by 20, the temperature of surrounding medium. And we are interested to simplify this one. I mean, it depends whether you take it to variable separable form or linear differential equation in the dependent variable capital T, whatever the procedure is there. If unit of time is minute, then T is going to be 120 when T is equal to 0, and of course after 10 minutes when T is equal to 10, capital T, temperature of coffee, calm down to 80. So the solution of the previous equation, solution of this equation, whatever the technique that you apply, it will turn out to be T minus 20 is equal to capital A e raised to power minus kt. Capital A stands for constant of integration, small k is constant of proportionality. Apply the first condition. What the first condition? Initially, it's basically the initial condition. When T is equal to 0, capital T is 120. T is 0 there. Capital T is 120. Simplify that to get down the value of one of the unknown. Capital A is going to be 100. Place this value over there. Now apply the second condition. When T is equal to 10 and capital T is equal to 80. So small t is 10, capital T is 80. Simplify that. Our target is to get rid of k basically, no? But you could also replace this whole factor e raised to power minus k. Whatever the possible way is there, our target, initially we get rid of capital A by applying one condition because there are two unknowns, capital A and small k. And we have two conditions. One condition is there and the second condition. Applying the first condition, we get rid of one of the unknown. No, our target is to get rid of k. But sometimes it is more viable if things are a bit messy, like in this case. I mean, in order to find the value of k, it is going to be more demanding. Why not we take the value of e raised to power minus k? Our target is to replace k. Eventually, this whole thing is going to be replaced, e raised to power minus k, by that one. If you replace it over there, so it will turn out to be t minus 20 is equal to 100 times that factor. Now you see that it's a relation between capital T and small t. What the task is there, if you look back, what will be the temperature of coffee after either we need to get rid of another or make it 10 minutes. Another 10 minutes means 10 minutes plus 10 minutes after 20 minutes. Initially, when T is equal to 0, temperature is 120. After 10 minutes, 80. After another 10 minutes. So it's a typographical error. So make it 10. Make it 10 over here. I will adjust it with the slides. So with your file, make it 10 or cancel this one, strike out another. So after another 10 minutes means when T is equal to 20 from the starting time. When T was 0, temperature is 120. After 10 minutes, temperature calm down to 80. No, after 20 minutes, we are expecting that temperature to be 56 degrees centigrade. Let's just plug in the value of T as 20 simplified. So hence the temperature of coffee after another 20 minutes, after another 10 minutes, in fact, sorry, another 10 minutes is approximately 56 degrees centigrade. That's a typographical error. It should be 10. So this is an idea. Practical demonstration is there from our daily life. Scenario is there. We make mathematical modeling, and then we look into the solution of the phenomena by solving that particular differential. Another example is there. A thermometer, the reading is 5 degrees centigrade, is brought into a room whose temperature is 22 degrees centigrade. I mean, the room temperature is there. 1 minute later, the thermometer reading is 12 degrees centigrade. Initially, it was, you see that, 5 degree, but because of the room temperature is much greater than the temperature of the thermometer, the body is going to heat up with the passage of time. The body is thermometer in this case. How long does it take until the reading is practically compatible with the room temperature? What the room temperature is, 22 degrees centigrade. Say 21.9 degrees centigrade. Because partway through the journey, I mean, you might get the answer undefined with 22 degrees centigrade. So you need to put in the value of room temperature as 21.9, the actual value centigrade. Thermometer will take approximately 9.68 minutes until the reading is compatible with room temperature. What the room temperature is generally 22 degrees centigrade, or effectively 21.9 degrees centigrade. One more challenging question is very, very interesting. I believe that the most interesting question you can ever have in your life. I mean, you see that you are just like playing the role of spy, just playing the role of like Scotland Yard, member of Scotland Yard, CID, for example, or whatever it is. I mean, the investigation officer, for example, or whatever it is. So, plenty of options for you to join the forces over there. But the scenario is there. I mean, the story is there. It's more like interesting story is there, happening all around us in this country, unfortunately. All right, what the practical demonstration is there. See, Asif Ali is the name of a student from BSc Engineering. Assume that BSc Electrical Engineering, session 9, 2019, for example. Is there any Asif Ali in your session? If there is, follow that person. Met his neighbor, Haji Bashir Hussain, after Isha prayer. Early in the morning, when he was ready to come to UET, Department of Electrical Engineering, he heard that Haji Bashir was murdered last night. Quite often we look into this scenario. Policemen were gathered, and for investigation purpose, they were interested to find the time of death of Haji Bashir Hussain. I mean, very practical demonstration for investigation purpose. They are interested to see the time of death. He was murdered last night. You knew that he was okay around Isha prayer. But early in the morning, when you are ready to come to UET, so you heard that Haji Bashir has gone. Asif Ali, as a name, arbitrary name, is known and expert in the theory of ordinary differential equation. He resolved the problem, and I mean, he solved this problem for those policemen, for those investigating institution, for those paramilitary forces. I mean, he solved this problem. What is the observation behind this? He went into the room when early in the morning, when he was just about to come to UET, at about 8:30 a.m., for example, he went into the room of Haji Bashir Hussain and found that temperature of the body is 80 degrees Fahrenheit. The time is here, 8:30. I mean, this is the time. The temperature of the room is kept constant at 60 degrees Fahrenheit. I mean, these are the observations. You take a note. Temperature of the body time, and then temperature of the room. 2 hours later, the temperature of the body dropped to 75 degrees Fahrenheit, from 80 to 75 degrees Fahrenheit. So the time, initial time, I mean, when t is equal to 0, it's 8:30 a.m. When t is equal to 0, temperature of the body is 80 degrees Fahrenheit, temperature of the surrounding medium 60 degrees Fahrenheit. After 2 hours, means at 10:30, temperature of the body dropped from 80 degrees Fahrenheit to 75 degrees Fahrenheit. Guess the time of death. Asif Ali calculated. Practical demonstration. I'll give you an idea. You have to investigate yourself. Pretty interesting. Pretty interesting. Scenario is there. I mean, we often read these kind of stories in the paper, electronic media is there, in our neighborhood, everywhere, sort of. So if things are happening like that, so being a mathematician, being an expert in the theory of ordinary differential equations, you should be able to handle those scenarios. You would be much appreciated, of course. All right, what the idea is there? I'll give you an idea. Assume that Haji Bashir Hussain was not sick. I mean, assume that he was okay. Because if this is the thing, temperature is going to be different. For a normal person, the temperature is going to be 98 degrees Fahrenheit. The initial temperature of the body, 98 degrees Fahrenheit. And temperature of the surrounding medium, 60 degrees Fahrenheit. You need to think about that. A bit challenging, but very, very interesting. All right, so that's it. We started off, I mean, things are more demanding, of course. When we look into the practical demonstration, you need to handle each and every scenario. Every scenario is different from the other. So, of course, it's not a thing that you just handle one or a couple of examples and then hundreds of examples could be given to the student. So, a bit more demanding, I believe that. So this is all. I mean, it's more challenging to look into the applications. So we started off talking about applications. There are quite a few. Next time we will try to look into few more applications from our daily life, in particular talking about electrical engineering. That's what we are looking for. All right, so that's it. If you have any query, got a few minutes before we officially wind up. Oh, interesting. Our engineers can't repair even a bulb after completing engineering. If you are just an engineer, we believe that this is the scenario. But the stronger you are in mathematics, the more the foundation of mathematics is there, the better the engineer you are. This is the takeaway of the day. You have to build better foundation in mathematics in comparison of the others. Of course, the others are vital, but the base is there in mathematics. Mathematics is the backbone of engineering. If you are lacking in that, so of course you won't be able to even repair a bulb. Alrighty, thank you very much. See you inshallah. Stay blessed. Assalamu alaikum wa rahmatullahi wa barakatuh.
Assalamu alaikum wa rahmatullahi wa barakatuh.